Hello, my name is Leah Segui, and I'm a policy fellow with GeoBlue Planet. The ocean connects us all, whether or not we live by it. It feeds us, supports our economies, we use it for recreation, and it has a big impact on our weather and our livelihoods. The more we understand about our ocean, the more we realize we need policies and management strategies for the resilience and sustainability of our planet. GEO's 3 engagement priorities, the Sendai Framework for Disaster Risk Reduction, the UN 2030 Agenda for Sustainable Development, and the Paris Climate Agreement, all depend on ocean and coastal information for implementation. The Sendai Framework seeks to reduce disaster risk through understanding vulnerabilities and enhancing disaster preparedness. For the 40% of the world's population that lives near the coast, there's a demand for ocean and coastal observations to implement the Sendai Framework for disasters such as coastal flooding, like in Indonesia seen here. We need these observations for the development of multi-hazard early warning systems, disaster risk information, and assessments. The 2030 Agenda for Sustainable Development are a set of global goals centered around the sustainability and health for communities and ecosystems. 17 are related to the ocean, and one of them, Sustainable Development Goal 14, or SDG 14, is explicitly for the conservation and sustainable use of oceans, seas, and marine resources. Ocean and coastal observations play a key role in monitoring the ocean-related targets and with helping nations make informed decisions to achieve these sustainability goals. This leads me to the work of the GeoBlue Planet Initiative, which is the ocean and coastal initiative of GEO, linking ocean and coastal information with society. We work in 10 thematic areas represented in the image here, and for today's talk, I will focus on 2 of them. First is our work on disaster warning and mitigation as it relates to the Sendai Framework, and second is our work on water quality as it relates to SDG 14, life below water. For disaster warning and mitigation, our focus is on low-lying islands with coral reefs that experience wave-driven flooding. These flood events could strike with no warning, even on windless, sunny days. Historically, this occurred every 20 to 30 years, but sea level rise will exacerbate the damage of wave-driven flood events on infrastructure, freshwater supplies, agriculture, and critical habitats. The image on the left is from Kiribati, and the 2 images on the right are from the Marshall Islands. And these illustrate the need for forecasting tools to protect the lives and livelihoods of coastal communities. There are challenges when it comes to forecasts for reef-line coasts. First, while there are forecast tools for sandy shorelines, they don't accurately predict wave flooding on reef-line coasts, leaving communities without proper forecasting tools. Second, the few models that do exist are expensive. And third, they require large amounts of computing power. We hope to address these challenges with WaveForce, which stands for Wave-Driven Flood Forecasting on Reef-Line Coasts Early Warning System. This is a collaboration with NOAA, USGS, Deltares, CSIRO, and other partners. WaveForce will be developed for all coral reef-line coasts throughout the world and will provide coastal flood forecasts 7.5 days in advance, every 3 hours. It'll be updated every 6 hours and given at intervals of 200 meters. The WaveForce system consists of 3 components, which are visualized here. First, altimeter satellites and models provide wave height and sea surface elevation forecasts. These 2 models, along with bathymetry, are inputs for a flood model. WaveForce then produces a forecast based on every wave height, sea surface elevation, and bathymetry combination. Since this output is a simple lookup table, it can be retrieved using a PC. This system can be used for both forecasts and hindcasts, which are both important for combining local knowledge and technology to support resilient coastal communities. Integration of satellite-derived wave height and bathymetry will be supported by the Committee on Earth Observation Satellites, Coastal Observation and Application Study Team, also known as CEOS Coast. We plan to engage with users and stakeholders to co-design products that are fit for purpose. I will now focus on our work relating to the UN SDG 14.1, which seeks to prevent and significantly reduce marine pollution of all kinds by 2025. The two indicators that we work on are 14.1.1 A and B, which focus on anthropogenic nutrient inputs and marine litter, respectively. We worked in collaboration with UN Environment and GeoAquaWatch to develop the methodology for the Index of Coastal Eutrophication. For marine litter, GeoBlue Planet has hosted a series of workshops funded by the IEEE Oceanic Engineering Society. And we have drafted a white paper outlining a concept for a global platform for monitoring marine litter and informing action at request of the UN Environment Program. For context, eutrophication is a process by which nutrient inputs into the coastal system cause excessive growth of marine plants, algae, and phytoplankton. You can see the red algae explosion on the right. These nutrients come from land-based sources, and in particular, nitrogen and phosphorus, from agricultural fertilizers, livestock waste, and detergents in domestic wastewater. As many countries do not have in situ nutrient data to assess eutrophication, we have worked with the UN Environment to support the development of sub-indicators related to chlorophyll A, which is a common indicator for eutrophication. Here's the methodology for the Index of Coastal Eutrophication. It is split into 3 levels: Level 1 for global, Level 2 for national, and Level 3 for supplementary indicators. This talk will highlight our work on Level 1 indicators, mainly the chlorophyll A deviations. Chlorophyll A deviations rely on remote sensing to determine the percentage of coastal zone with chlorophyll A deviations and intra-annual coastal zone chlorophyll A anomalies. For this first one, it uses an ESA Ocean Color CCI product seen here on the right. This is led by the Plymouth Marine Lab, and they use ocean color imagery from SeaWiFS, MODIS, MARIS, and VIRUS from 1997 to 2019 to produce a merged chlorophyll A product. To determine the percentage of coastal zone with chlorophyll A deviations, we use chlorophyll A derived from the Ocean Color CCI product. So let's say you are interested in deviations in 2018. Chlorophyll A is generated for each individual pixel within a country's coastal zone for the reporting year. This is done monthly with a 4-kilometer resolution. For generation of a baseline, results are averaged by month between 2000 and 2004. We then use these values to calculate a percentage of coastal zone with chlorophyll A deviations seen here, which is the average monthly pixel chlorophyll A from the baseline minus that from the reporting year divided by the baseline, multiplied by 100. We use these data to generate a chlorophyll A dashboard seen here. We are working with Esri to produce statistics and develop visualization tools for UN countries to identify potential eutrophication hotspots within their coastal zones. The goal is to show trends in chlorophyll A and to help inform in situ collection of nutrient data. Ultimately, we want to be able to link eutrophication hotspots with additional information, such as river inputs and land use changes. We are currently brainstorming ideas of how to use machine learning to integrate these different data sets. For intra-annual coastal zone chlorophyll A anomalies, we use NOAA VIR's chlorophyll anomaly products that are calculated using a running 61-day chlorophyll A median. We could first calculate the relative frequency of chlorophyll A anomalies by dividing the number of days with a high anomaly by the number of days with valid observations. The cumulative relative frequency is calculated similarly, and it's based on the range of values associated with each level of anomaly. So from no anomaly, moderate, high, to extreme. The cumulative relative frequency could be used as a visualization tool to show anomaly occurrences at a given location. Lastly is our work on marine litter, a global issue spanning from land to the depths of the ocean and even on the most remote islands. We address this through a white paper titled, "A Global Platform for Monitoring Marine Litter and Informing Action." The white paper covers 6 topics. First, it provides a review of existing and developing monitoring technologies, from human observations to remote sensing of floating plastic seen here. And this image is from Dr. Laura Bierman et al. 2020. The white paper also provides a review of existing marine litter databases and major published datasets, such as the Global Ghost Gear Initiative data portal seen here. It includes SDG indicators and other types of indicators, a review on monitoring the plastics value chain through a life cycle approach, and we identify existing and developing global platforms to share data. So with all these data and technologies that may not be interoperable, this presents an opportunity to leverage advances in machine learning and AI to harness these different sources and tools to combat marine litter. So lastly, UN Environment and IBM are developing a multi-stakeholder platform that will capture and integrate various elements of marine litter that could be used by anyone, from the general public to scientists to decision makers. Their current focus is establishing national baselines for marine litter for countries to understand their largest sources of litter and to measure policy effectiveness. Along with our work in support of UN and SDGs, GeoBlue Planet also provides networking and coordination support to connect the marine litter community. We also work with stakeholders at global, regional, and local scales to identify data and information gaps, and to help identify best practices in marine litter related to ocean observations to inform policy and measure their effects. I also want to highlight work done by steering committee member Eric Chassanet and his colleagues on modeling the movement of marine plastic waste, which is another project funded by the UN Environment. This project aimed to determine where plastic waste went once it was released into the ocean and where plastic waste on coast come from. To do so, they used particle seeding that realistically represents the input of mismanaged waste into the ocean, was then combined with a high-resolution global ocean circulation and wind data, as well as a state-of-the-art Lagrangian analysis tool called Ocean Parcels. The web interface of the model is seen here. And the colorful lines represent plastic waste movement from 2010 to 2014. The models show that about a quarter of marine plastic waste released into the ocean stays in the ocean, whereas 3/4 of it ends up on the beach. The waste that remains in the ocean accumulated primarily in the subtropical gyres, Mediterranean Sea, and in the northern Indian Ocean, especially in the Bay of Bengal. And this is consistent with anecdotal and published observations. You can check out the model at the address seen below. The integration of ocean and coastal data is key to achieving the global policy frameworks addressed in this talk. These global policies illustrate the need for the integration of Earth observations from land to sea to inform policy and management solutions. GEO is in a great position to use the upcoming UN Decade of Ocean Science for Sustainable Development to make progress on global policy frameworks and inform regional and national policies and management strategies. GEO's cross-cutting nature provides the opportunity to support the decade by integrating data across the land and sea interface and harness its global partnerships, pursue concrete actions, and use Earth observations in service to society. Management and policy decisions related to the successful implementation of the Sendai Framework and the UN 2030 Agenda will continue to depend on Earth observations. But the science is not enough. We also need to integrate knowledge of socioeconomic systems and the human dimensions that influence how we are impacted by and how we impact the ocean. We invite you to continue the conversation on integrating water and coastal datasets at the 5th GeoBlue Planet Symposium in South Africa in 2021. Thank you.